So good afternoon, everyone. Welcome to this NITheCS Colloquium. Today, it's a real pleasure to welcome Dr. Ryan Sweke. As a speaker, Ryan was a PhD student at UKZN when I was also still there. And after completing his study, he went for a postdoc to Berlin. And now he's working for IBM in California. Yeah? And he's speaking to us. Okay, you can't see him now, but at some stage you will see him. Yeah, he's speaking to us from California this afternoon. Yeah. So Ryan, we are very, very happy that you accepted to give us a talk to a topic that is close to all our hearts. Yeah. And if you are ready, we are ready to watch your presentation. Thank you very much, Ryan.
Great, thanks, Francesco. Okay, so I'm going to assume that everybody can hear me and see me. Great, cool. So I'm very happy to be invited to give this seminar. Thanks a lot, Francesco, and to NITheCS. Today I'm going to speak about quantum machine learning with parameterized quantum circuits, which is something I've worked on with many collaborators over the last few years. And because I suspect that the audience is extremely varied, and probably there are many people who do not have a background in quantum computing or who do not even know what a quantum computer is, I'm going to start with a very quick, very basic introduction to the very fundamentals. And so the first question we need to understand is, what is a quantum computer, if we're going to be able to follow a discussion about quantum machine learning? And so at a very high level, what a quantum computer is it's a scalable, I'm going to give a criteria that that things should satisfy in order to be a quantum computer. So in order to be a quantum computer, a device should consist of a scalable collection of stable qubits, where a qubit is nothing but a two-level quantum system. So if you've taken an introductory quantum mechanics course, you just think about a quantum system that lives in C2, and its state is the superposition of a basis state 0 and a basis state 1. So that's a qubit. And a quantum computer should consist of some collection of qubits realized in some physical system. Then the second thing a quantum computer should be able to do or should consist of is the ability to prepare some fixed simple input state. So for instance, we often represent that using figures like this. Here we imagine that we have 4 states fixed into the basis state 0, and these lines are going to represent their time evolution. Okay, so we assume that our computer consists of qubits and that we can prepare fixed input states. And then importantly, what we need is the ability to implement arbitrary unitary operations. So we're going to represent this with a box acting on the qubits. And finally, to get information out of the computer, we're going to have the ability to make qubit-specific measurements. And we normally denote that with some sort of measuring device. Now, as hopefully some of you know from the sort of foundations of quantum mechanics, when you measure quantum mechanical systems, what happens is you get some outcome from some probability distribution. So here, the probability, if you make a measurement in the computational basis, the probability of getting some bit string x is given by this expression here, and every measurement you make is going to sample from this probability distribution. And now the idea of quantum computing is that the computation is defined by the unitary operation. When you write a computer program in Python or something like this, the computation is defined by some sequence of bits in your computer turning on and off. And in quantum computation, you define the program by specifying the unitary operation that's applied to your qubits. And then the solution is defined by the probability distribution over the measurement outcomes. You can imagine each of these bit strings as encoding some potential solution. And you want to choose a unitary such that the output probability distribution is peaked on the solution to the problem, so that when you measure the system, you're most likely to get the correct answer. So at a very high level, this is what a quantum computer is. It's a collection of qubits, which are two-level quantum systems, which you can prepare in some fixed simple input state, you can manipulate by applying unitary operations, and you can measure in the end to get out the information about the system. So that's a quantum computer from the high-level perspective that we're going to need. All right. And now the important thing is that we have to be able to implement arbitrary unitary operations, but this sounds complicated. I mean, if you do a counting argument, there's infinitely many unitary operations. So it seems unlikely that we can design a device that can just implement any unitary operation. And the key insight that makes this all possible is that actually we can come up with so-called universal gate sets, and there exists a gate called the C0 gate and single qubit gates that form one. And what I mean by this is that any unitary you can think of can be written down as a sequence of C0 gates, which are these gates here, which entangle qubits, and single qubit operations. So boxes which only operate on a single qubit. And suddenly this seems much more likely. Single qubit operations, there's a much smaller number of them. We only have to manipulate single qubits, and C0 gates are just one gate that we can focus on easily. So the point is that in order to implement arbitrary unitaries, it's sufficient to be able to implement C0 gates and single qubit operations. And so we can update our criteria to from quantum computers need to be able to implement arbitrary unitary operations to quantum computers need to be able to implement at least one universal gate. Okay, now the point is that once we've written down a unitary in terms of a sequence of gates from a universal gate set, we can start to talk about something called the circuit depth, which is essentially the number of layers of gates that we need to implement in order to implement the unitary that that defines the program that we're interested. And this allows us to define the whole field of quantum complexity theory. And the key thing that we're interested in here is the circuit depth. We need a notion of efficiency. When is a program going to be efficient? When is a program going to be not efficient? And we're going to say that any quantum computation defined by a unitary which admits a decomposition into universal gate sets such that the circuit depth is a polynomial function of the size of the problem, so we can think roughly about the number of qubits, then we will think of that computation as being an efficient computation, one that we feel is plausible to run. And this is kind of standard in complexity theory, where you think that in order to consider a program efficient, the amount of time it takes to run should be some polynomial or slow-growing function with respect to the size of the problem. Okay. And so now we can ask, now that we have a notion of complexity for quantum computing, what is the power of quantum computing? Why do we think that it might be a good idea to build quantum computers? Why do we think they might offer us any advantage over traditional computers? So the two most famous complexity classes for classical computers are these classes P and NP. So roughly, if you haven't heard of these, you can think about P as containing the set of all problems that we can imagine can be solved easily by regular computers. And we can think of NP, which is technically the class of all problems where the solution can be checked efficiently by a classical computer, but not necessarily efficiently found. You can think of NP as being emblematic of problems that are hard for classical computers. So think about something like traveling salesman problem, something where you more or less have to do a brute force search if you want the answer. And then there's a class called the NP complete problems, and these are somehow the hardest problems in NP. And they have the property that if you come up with an algorithm to solve one of them, then you can solve any problem in NP. So there's some problems in NP which are somehow as hard as it's possible to be while in NP, and there are some that are easier, ones where if you solve them, you wouldn't necessarily be able to solve any other one. And we believe that quantum computers can solve the set of problems in this dashed line. And we call this class PQP for bounded quantum polynomial time. And the very important point is that we do not believe that quantum computers are going to be able to solve all problems in NP. In other words, we don't believe that there's an NP complete problem that quantum computers are going to solve. And by solve, I mean have a unitary operation which defines a program such that that unitary operation has polynomial depth circuits. But we do know that there is one problem, factoring, which sits in the sweet spot for which they do exist efficient quantum algorithms. And we think that we should be looking for other problems in the sweet spot, problems that we know that we don't know how to do yet with a classical computer, so they're not in P. So they should be in NP, but they shouldn't be the hardest possible problems in NP. And other problems in this class include things like graph isomorphism. Okay, so now I feel like we have a good high-level overview of what a quantum computer is, what sort of problems we think they might be able to solve, and we have some good motivation for building one, because this class PQP is bigger than the class P. Okay, so what's the problem? Why don't we have massive quantum computers factoring numbers right now? The issue is that to build a quantum computer, you have to have a physical system which realizes these qubits. You have to have collections of physical systems which realize these two-level systems, and then you have to apply a gate to these qubits over time. So this might be a circuit that you want to implement that might do something. And so you might start by preparing the qubits, you might prepare a layer of gates, but then unfortunately, because of the fact that these gates and these qubits are subject to the influence of the outside world, to electromagnetic radiation, to vibrations, etc., errors are going to occur in your circuits. And errors, you can think of some sort of generalized gate that's out of your control, and you don't know what happens. And the problem is that if enough of them occur, then the program that's effectively run is completely different to the one that you want it to. And unfortunately, errors are an unavoidable source of frustration for people trying to build quantum computers. And so we have to have ways of dealing with them and getting around this issue. But luckily, since the early 90s, people have known more or less how to do this with something called quantum error correction. Okay, so this is a bad situation. We want a good situation. And the idea of quantum error correction is instead of having one two-level system for every qubit, what you do is you group many qubits together. So now the states live in a much higher dimensional space, and you call the zero state some small subspace of this 3-qubit state. So here, for instance, for every qubit, I've created 3 qubits, and I define the zero as the ground state of some Hamiltonian acting on these 3 states. It's not necessary to follow the details. All I want you to get from this is that you create many qubits in place of one. So this is similar to how if I want to send you the message 0 over a channel that might flip the bit from 0 to 1, I can encode this message by sending you the 5 bits 0, 0, 0, 0. Okay, so this is what we do. We have some qubit overhead, and then you apply your gate. And now the clever thing you can do is, so some noise happens. The clever thing you can do is there's a sequence of clever measurements that you can make on the state that you can send into a classical computer, which can then run something called the decoding algorithm, which can figure out which operations you should apply to your collection of qubits, such that what comes out afterwards is the state that you want. So this whole process of defining the method of encoding one qubit into many and defining the decoding algorithm that goes on in this classical computer is called quantum error correction. And we have many schemes for doing this. And using these, you can continue to just correct errors as they occur in such a way that at the end, you have the actual output of the program that you want appearing here. The problem is that this requires a very large qubit overhead. And so at the moment, maybe we can implement quantum computers with 100 qubits, but in order to do computations using, we call these qubits here logical qubits, using 100 logical qubits, we might need something like 10,000 qubits, which is very out of range at the moment. Okay, so because of this, there's a natural question, which is what should we do with near-term quantum devices? Is there anything interesting we can do with the devices we actually have available now? At IBM, there are many quantum computers ranging from 16 qubits to 400. And on all of those devices, we are not capable of doing error-corrected computation. But is there something we can do with them right now? So what can we do with circuits that have limited circuit depth? And these devices are typically characterized by having on the order of 100 qubits. There's no full-fledged error correction, but we can do something called error mitigation, which is some sort of classical post-processing, which allows us to kind of figure out to some extent what errors happened and correct for them, but you can't scale this. The cost of error mitigation is much too expensive to ever use for general purpose computation. And the error rates only allow us to implement circuits of depth 10 to 100. In other words, the errors accumulate so fast that as soon as you're at, let's say, 50 qubits, 50 layers of gates, you've completely scrambled the computation that you're interested in. So what can we do with these devices? And it turns out that one of the primary things that people have investigated for as an application of these near-term quantum devices is something called variational quantum machine learning. And the idea of variational quantum machine learning is to take quantum circuits and to parameterize their gates and to use these so-called parameterized quantum circuits to define learning models. So there's a lot of jargon in this box, and let me walk you through it so that we can get a better idea of what this actually means. So imagine I have a quantum circuit, and now we know that any circuit consists of single qubit gates and CNOTs, let's say. And now imagine that the first operation, so there are the Pauli matrices X, Y, and Z. These are single qubit operations that you can apply to qubits, and you can also time evolve qubits using the Hamiltonian Pauli X, Y, or Z for different amounts of time. So imagine this RY gate basically says that I want to implement the time evolution under the Hamiltonian Y for a time period of x1. And this gate says I want to implement time evolution under the Hamiltonian Z for amount of time x2. And the idea is, imagine we want to define a function from x to some output. What we can do is we can input that classical data into the circuit by parameterizing some of our gates by the classical data. And similarly, we can parameterize some of the gates by variational parameters that we want to tune. So at a very high level, what we do is we have a quantum circuit where some of the gates are parameterized by data, x, and some of the gates are parameterized by trainable parameters, which we call theta. And in the end, we get a unitary operation which depends on the classical data and some trainable parameters. And now we can easily define a function, like parameterized function from this circuit. And the idea is you start in the all zero state. There's a typo here, this should not have a dagger, but you start in the all zero state, you apply the unitary operation defined by this circuit, you measure an observable, let's say the Pauli operator Z on this first qubit, and then you ask for the expectation value of that measurement. And this is going to be some number between -1 and 1. So you see that to each class of circuits, we can associate, or to each circuit, or each instance of the parameters theta, we can associate a function. And so any circuit which is parameterized, or any circuit whose gates depend on parameters that we can tune, we call a parameterized circuit. And from parameterized quantum circuits, we can define functions. And then what we're going to do is we're going to use the quantum computer to evaluate some loss function. So for instance, if you're doing supervised learning, you're often interested in how some label y compares to the output of some function that you're learning, f of theta, and you might use this 2 norm to compare the difference. And then you feed that loss function into a classical computer, and the classical computer is going to figure out how you should update the parameters of your circuit. And so the point I want to make is that this is exactly analogous to how neural networks work. In a neural network, the weights of the connections in the neural network are the parameters, and for each instance of the parameters, you have a function, and then you run that function enough times to determine a loss function, and then there's a rule, which is stochastic gradient descent, typically, that tells you how to update the parameters. And so this is an appealing suggestion for how to use near-term quantum devices, because we don't actually know which computation we want to implement. We want to learn it. And so maybe in doing that, we can also take into account the noise that is happening. We learn the best parameters, taking into account the noise that is occurring in the device. Okay. So there's this idea of variational quantum machine learning, in which we treat quantum circuits basically equivalently to how we treat neural networks, and we want to train them to find the solution to problems. But what do we want? Like, as a theorist, as a mathematician, as a theoretical computer scientist, what would we like to do, or what would we like to show in both machine learning or quantum machine learning? And ideally, what we would want to do is we would want to get rigorous guarantees for state-of-the-art learning frameworks on real-world data sets. So what I mean is, we would like to take some data set like the stock market or protein configurations. We would like to consider some classical model like a neural network or a graphical model, some state-of-the-art algorithm like stochastic gradient descent, or this expectation maximization is how you train probabilistic graphical models. And we would like to be able to say that in the worst case, I need this amount of data in order to guarantee that my algorithm will get at least this accuracy. That's the kind of thing that we would like to do. We would like to have theorems which guarantee us that. So we know in practice how much data we need and how accurate we can expect our model to be. But now, as people doing quantum machine learning, we want that not only for classical models, but also for quantum models, like parameterized quantum circuits, interacting with some learning algorithm like stochastic gradient descent. Okay, this is our job as theorists working on quantum machine learning, to derive rigorous guarantees for state-of-the-art learning frameworks on real-world datasets. But even better would be if we could find some separation between the power of quantum and classical learning. So imagine this is some scale which represents the amount of data that an algorithm needs. And imagine we could prove that in order to achieve a certain accuracy, classical algorithms need at least some amount of data. What we would like to do in order to motivate quantum machine learning as an application is prove that there's some quantum machine learning algorithm which needs at most some amount of data, which is less than the classical algorithm needs. And we call this gap a quantum classical separation. And this would provide a very, very, very concrete motivation for doing quantum machine learning or for building these devices. Okay, we could also do the same thing with accuracy. And in this case, what we want is a guarantee that a quantum algorithm with some fixed amount of data will be able to achieve at least some accuracy, whereas a classical device will be able to achieve at most some accuracy. So this is what we want. We want to analyze real-world data sets, state-of-the-art models, and prove theorems about quantum classical separations. Unfortunately, this is extremely hard, even for purely classical models like neural networks. Proving lower bounds on the amount of data or upper bounds on the accuracy from sort of first principles is something that people really struggle with. It's sort of at the forefront of classical machine learning doing that. So what can we do? Because we still have no idea whether quantum computers should be used for variational quantum machine learning. I mean, of course, we can write down this idea, but is this sensible? Is there any good reason to do this? Well, to get some intuition, as a first step, what we could do is we could relax some of the ideal requirements. So instead of considering real-world data sets and sort of state-of-the-art learning algorithms, we could ask, is there some fine-tuned data set, so some sort of data set that's rigged or that we constructed by hand, and we can consider fine-tuned learning algorithms, and we can ask whether you can get a quantum advantage in learning in this sort of setting. So for instance, some of you might have heard of the problem of discrete logarithms. So this is a computational problem that we think is hard and whose assumed hardness is at the basis of a lot of cryptography. So we could ask, is there some way we can embed the discrete logarithm problem into a data set, and then come up with a very specific quantum algorithm and compare that against classical algorithms and get an advantage in this case? And so if you are willing to consider fine-tuned data sets and fine-tuned learning algorithms, then one can actually prove that there exist learning problems, not natural learning problems, not learning problems that appear in the world, learning problems that someone constructed by hand purely to prove that a quantum computer can do better than a classical one. But you can prove that these exist, and the quantum algorithms can give a rigorous, proven quantum advantage. So the important thing to realize about these results is that they don't provide any evidence that the sort of generic quantum learners that I spoke about before, those that are defined by parameterized quantum circuits, they give no evidence that generic quantum learners will give an advantage on real-world problems. But you can think of this as a sort of necessary condition. In other words, imagine I'm unable to prove that quantum computers can do better at machine learning, even for some extremely fine-tuned task that is biased in their favor. If they can't do this, then I should be very skeptical that they're going to succeed on real-world problems that have much less structure and against which they're competing against things like neural networks. So this is somehow a necessary condition and a first step that people had to go through, and you can see these papers here to see an example of how you use cryptographic tools to build machine learning problems that you can prove quantum computers have an advantage over classical computers. Okay, so this is what we can do, and this has been done for reinforcement learning, for distribution learning, for supervised learning. And this has given us the sort of insights that it's not completely ridiculous to look at quantum machine learning, in the sense that we know that quantum computers can at least get some advantage for fine-tuned problems. But we want to now turn our attention back to variational QML. In other words, the study of parameterized quantum circuits, or in particular to this framework of classical computers interacting with parameterized quantum circuits. You run the parameterized quantum circuit to evaluate a function. You send the last function into a classical computer, which tells you how to update the circuit. We want to turn our attention back to these sorts of models. And as a theorist, the sort of questions we're interested in is, what class of functions can these models represent? We would like to understand the class of functions they can represent. And importantly, we would like to understand their merits relative to classical methods. We would like to understand, in a sort of theoretical way, how they compare to things like neural networks or kernel methods, stuff that people doing classical machine learning are familiar with. Because ultimately, if we can prove that a parameterized quantum circuit can never do better than some simple neural network, then we know that there's no point in using this. But it seems like before we can do that, we should at least understand the class of functions that they can represent and how this compares to something like neural networks. Okay, and in this talk, or the time that's left in this talk, I'm going to explore both of these questions. Okay, so first let's ask about the expressive power of variational quantum machine learning. In other words, what is the class of functions that these methods can represent? Okay, and we're going to consider models of the following type. So we're going to consider parameterized quantum circuits that consist of two types of gates. Okay, you measure them at the end. And the important point is that some of the gates are parameterized by data, which is represented by X. And some of the gates are parameterized by parameters theta, which are going to be updated during the training. So basically, these encoding gates tell me how I put the input into the circuit, and the trainable gates get updated. And then there's gates W, which are fixed. You can think of these maybe as gates that entangle all the qubits in a sort of deterministic way. And these circuits define a unitary which depends both on data and trainable parameters. And like we know, or as I said before, we're going to define functions from these circuits by saying that the function we're interested in is the expectation value of the observable that we measure, which is typically something between -1 and 1. So these sort of circuits are sometimes called re-uploading models because of the fact that the data doesn't just enter in at the beginning, but you can, at any point in the circuit, implement or insert a gate which encodes the data, which sort of re-uploads the data into the circuit. Okay, so we have these circuits. Some of the gates depend on data, some of the gates depend on trainable parameters. And we're going to make one more assumption, that the gates which depend on data all have the exact same form. They all implement the time evolution of some Hamiltonian X for a duration of time, which is determined by the data point. So this is called the Hamiltonian encoding, and it's very natural because in laboratories like at IBM, we know exactly which Hamiltonians we can perform time evolution of. And we basically say that what determines the gate, and we basically going to say that we're going to use the data simply to determine how long we should turn on a specific Hamiltonian for. So on this qubit, when it gets here, like xj, the jth component of our data set, is just going to tell us how long we run some specific Hamiltonian h for. So we're going to assume that all the encoding gates have that form. And now let's say, sorry, I've got another typo here. This should be x1 to xd. So we can imagine that the data is a vector, a d-dimensional vector. Think about that as a d. And we can imagine that for x1, there is some set of Hamiltonians, let's say n different Hamiltonians, that we use to encode the data point x1. And we can imagine for each data component, there's some set of Hamiltonians. For instance, then for xd, there's another set of Hamiltonians that at some point we use to encode the data component xd. And we call this collection of Hamiltonians, the set of Hamiltonians that we've used at some point to encode the data, a data encoding strategy. If we're only allowed to use gates of this form, then essentially what determines our strategy for encoding data is the choice of Hamiltonians that we make. Okay, so now we have a sort of main result about these models, which is that for any variational quantum circuit, which depends only on data encoding gates, trainable gates, and fixed gates, where the data encoding gates have that Hamiltonian encoding form I mentioned, we know that these define some function, f of x parameterized by theta. And the result is that we can show that all of these functions can be written in this form. So let's unpack it. So this is a sum over vectors, which we're going to call frequency vectors, and then some weight of the exponential of the complex exponential of the inner product of that weight with the classical data point. So if you've done some Fourier analysis, this should look very much to like a multi-dimensional Fourier series, but with only some very specific terms. In a multi-dimensional Fourier series, this would be over all d-dimensional, non-zero d-dimensional integer vectors here. But here we have this multi-dimensional Fourier series, but with some very specific set of frequency vectors W. And you can see this result proven in this paper here. And the key point, the key insight is that you can show that this subset of frequencies or frequency vectors, which determines the the function that can be expressed depends only on the data encoding strategy. It depends only on the data encoding gates. And these weights that weight each of these exponential terms depends on the trainable gates. So this is very nice. This tells us that if no matter which variational quantum circuit you give me, I know that there is some partial Fourier sum representation, which only consists of some very specific frequencies, and which frequencies it consists of depends on the Hamiltonians that I've used for the data encoding strategy. Okay, so the key thing here is this capital omega, which is the set of frequency vectors. Okay, so to give you some better intuition, let's look in 1D. So imagine we have data that just lives on the line. In this case, our function has this form. So now this should look very familiar to you from Fourier analysis. You have a sum over complex exponentials of different frequencies, and each one of those frequencies is weighted by a coefficient which depends on the trainable gate theta. Okay, and now in the 1D case, instead of having the sum over all frequencies, all integers, which is what you need to, which is what happens when you do a Fourier transform typically, we're only going to have a sum over some fixed n omega number of frequencies. So basically, to put it another way, you can imagine that your circuit consists of these gates here, they're called S, which depend on the data. And what these gates do is they fix the frequencies that are allowed. So maybe in this circuit, we end up that there's only 3 frequencies allowed. Omega 1 is that frequency, omega 2 is that frequency, omega 3 is that frequency. So which frequencies are allowed in the sum is completely determined by the data encoding gates. And sort of the strength of those frequencies, how much they're expressed in the sum, is determined by the trainable gates. And so this is a very nice insight, because objects like this are things that people have studied a lot in mathematics, applied mathematics, computer science. We're very familiar with these sorts of expressions and how to manipulate them and how to prove things about them. Okay, so remember the key thing that we're interested in is this set omega, the set of frequencies. So we know that any QML model defined from a parameterized quantum circuit can be expressed as a sum of these complex exponentials with this frequency vector, and we want to understand which frequencies should appear. And this slide's a bit technical, so maybe I'll go fast. But the point is that this set omega, we can prove that it's always the Cartesian product of d sets, where omega 1 encodes only the frequencies relative to the first parameter of the data, and omega d only encodes the frequencies corresponding to the dth component of the data. So we know it has this product structure, and because of that, we're only interested in understanding one of them. And we can show that the frequencies corresponding to the jth component of the data is defined by the set of all differences between some object capital lambda, and that capital lambda is basically the sum of the eigenvalues of the Hamiltonians involved in encoding that qubit. Okay, so this is completely hard to interpret from there, but basically imagine in your data encoding strategy for component J, you have 3 Hamiltonians, H1, H2, and H3. Imagine H1 has 3 eigenvalues, lambda 1, lambda 2, and lambda 3. H2 has 2 eigenvalues. This is lambda 1 and 2, and H3 has 3 eigenvalues. What you do is you create this tree, and in each leaf of the tree, you get a sum of an eigenvalue from H1, an eigenvalue from H2, and an eigenvalue from H3. So this lambda 111 is the sum of eigenvalue 1 from the first Hamiltonian, eigenvalue 2 from the second, eigenvalue 1 from the second, and eigenvalue 1 from the third. And basically what this expression here is saying is that the frequency set corresponding to the jth component is the set of all differences between all possible leaves of this tree. And so now you can see it's very clear that when you fix the Hamiltonians all have a spectra, and the set of differences between all possible sums of eigenvalues of Hamiltonians defines the frequencies that are accessible to the jth component. And the product of all of those for each component gives you the frequency set that appears here. Okay, this is probably much too technical to follow now live. The point I wanted to make is that all variational quantum models have this form where the frequencies that are accessible are determined purely by the Hamiltonians in the data encoding strategy. Okay, so again, to get some examples, Pauli matrix encodings are a neat special case. So imagine the Hamiltonians are all Pauli matrices, X, Y, or Z, which is something that's practically very relevant because time evolutions according to these Hamiltonians are things that we can do very easily in practice on quantum devices. And in this case, we find that the frequency spectrum corresponding to the Jth component just consists of integers between some minus nj to nj, where nj is simply the number of encoding gates for xj. So if every Hamiltonian in the data encoding strategy is a Pauli matrix, then we see that the frequency set consists of all frequencies from minus the number of encoding gates to the number of encoding gates. And as a very cool corollary of this fact, we can prove that parameterized quantum circuit models with appropriate encodings like Pauli matrix encodings are universal function approximators. In other words, in the asymptotic limit of infinite number of qubits, an infinite number of encoding gates, we can express any function we like with PQC models. And how do we prove this? Well, we know that any function has a representation via the Fourier transform. We can take the Fourier transform of any function and get a representation as an integral or a sum of the complex exponentials. And basically, we can see that if we just put more and more and more Pauli gates, then we can get the entire integers as a frequency spectrum. And then we can also prove that if the trainable blocks are expressive enough, you can realize any weighting of those frequencies. Okay, so already we see that this kind of new functional analytic way of understanding the class of functions which can be represented by parameterized quantum circuit models gives us a very concrete insight into these things, which is not obvious beforehand. If you just define these variational quantum models, it's not at all obvious that they can represent any function. But now, by gaining some insight into the structure of the functions they can represent, it's relatively straightforward to show that in the asymptotic limit, they are universal. And this is very analogous to a similar theorem for neural networks, which says that neural networks can represent any function if you allow the width to become infinite. This is kind of the analog of this neural network universality for parameterized quantum circuits. Okay, so now I'm going to get onto the second thing I wanted to speak about, which is the sort of comparison between parameterized quantum circuit models and state-of-the-art classical methods. And this is going to the title of this is called Dequantizing Variational QML, and you'll understand what I mean soon. So in order to obtain a quantum advantage using parameterized quantum circuit models or using quantum computers at all, it's essential that one needs to outperform all classical methods. If there's a classical method which does just as well as the algorithm you have in mind, there is no point to use a quantum computer. Remember, I showed these complexity classes. What makes quantum computing interesting is the fact that we believe that there's problems that quantum computers solve that are out of reach of all possible classical methods. And in machine learning, we kind of need the same sort of motivation. In order to use this, we want to be convinced that they're going to outperform state-of-the-art neural networks, kernel methods, etc. But rigorous analytic comparisons can be hard. So, I mean, the first thing that you would like to compare against is transformers, for example. These are all the rage in classical machine learning at the moment. But transformers are extremely complicated objects. We have some insight now into parameterized quantum circuits, but it's not clear how to prove theorems about the relative advantages and merits of parameterized quantum circuits and transformers. So dequantization is a good place to start. What does dequantization mean? Dequantization is the process of looking at your quantum algorithm and seeing if there's any places where you can sort of take the quantumness away and replace it with the classical algorithm, but maintain the same algorithm. In other words, can we start from our quantum learning algorithms and identify quantum-inspired classical methods that we think do just as well, and then analyze this? So basically, let's narrow the search space from every possible classical method to classical methods which seem to work in the same way that these quantum methods do, because this seems like a good way to construct classical methods that we can compare with the quantum methods. Okay, so we're going to do this for variational QML, exploiting our knowledge of the expressivity of parameterized quantum circuits. We're going to try dequantize variational QML. Okay, so the first thing that we should do, or that we can do when we try to do this, is we can note that parameterized quantum circuit models are linear models with respect to a feature map. So what does this mean? This is a lot of jargon. we know that any parameterized quantum circuit model can be represented by this weighted sum of complex exponentials. And we can expand these complex exponentials into causes and sines. And then what we can do is we see that we can rewrite this as an inner product between some vector which depends only on the data and some vector which depends only on variational parameters. So how do we do that? Well, we just say that imagine a vector which depends on x and maps x into cos of the inner product of omega-1, sine of the inner product of omega-1 and x, and then all the way up to the inner product or cos of the inner product of omega d, the dth frequency in x and sine. So this is a vector that just consists of cos sine, cos sine, cos sine, cos sine, and each pair of terms just has a different frequency appearing here. And then this vector of coefficients is just the a omega and b omega that appear here. So you can convince yourself that this expression here is identical to this expression here if you use this way of constructing these vectors. And this is by definition a linear model. What we mean by a linear model is a model that's defined by an inner product in this way. Okay. So what's very important though is that, so now we know that parameterized quantum circuit models, we know not only that they're weighted sums of complex exponentials, but we also know that they're linear models with respect to that feature map, the feature map that maps into pairs of cos and sines of different frequencies. But the important thing is that parameterized quantum circuit models can't realize all linear models with respect to the feature map. So if we think that we imagine some abstract space of all linear models with respect to the feature map. So what that is basically is the space of models defined by any where you can put any vector here. So this vector, the W, the vector of weights, is what defines the model. And basically the space of all linear models is just the space consisting of every possible, of all functions defined by any possible weight vector omega. And the point is that PQC models are a subset of this because of the fact that these vectors, which define the linear model, the coefficients that you can obtain in there are constrained by the architecture of the circuit and by how many trainable gates you have and what form they are. And the point is that we know that PQC models are a subset of all the linear models, but it's not well understood which subset. In other words, if you give me a quantum circuit, I can easily calculate the frequency set. In other words, which frequencies will appear in the weighted sum of exponential frequencies, but what weights are allowed, I don't understand. I know that in the limit of an exponential number of encoding gates, I can get anything here, but for some fixed sub-exponential depth, I don't know what frequency subset can appear here. Anyway, so the point is that there's some set of linear models, the PQC models are a subset of them, and when we do variational QML, implicitly what we're doing is searching for the best linear model in the subset of PQC models. So we might start from some set of parameters, we do a gradient-based optimization, we find another set, another gradient-based optimization, we find another set, and eventually maybe we converge to this model here. But kind of zooming out, we can see that what parameterized quantum circuit models are doing is implementing a variational search within some subset of linear models with respect to this feature map of alternating cosine and sine terms. Okay, and so for those of you that do classical machine learning, you should be immediately reminded of kernel methods. And let me remind you what a kernel method is, or show you what it is if you haven't done this before. So imagine you have some data living in a plane. What a kernel method does is it tries to find the line or the hyperplane which you can draw, the linear model, which best separates the data into two classes. So imagine the circles represent dogs and the x's represent cats. In 2 dimensions, we can easily see that there's no line we're going to be able to draw that will separate the dogs and the cats. And so the idea of kernel methods is to define a feature map. So a mapping from here, like R2, let's say, to R3. So I'm mapping from the original space the data lives into some higher dimensional space, such that in the higher dimensional space, there is a hyperplane or a linear model which separates the data. Okay, so this is kind of the idea of kernel methods. In kernel methods, which are closely related to support vector machines, we're always looking for a linear model, but we accept that a linear model might not exist for our data as it is. So we might want to apply some feature map, some mapping to the data into a new space in which a linear separator exists. And there is 30, 40 years of theory about kernel methods, and we know efficient classical algorithms to find the optimal hyperplane in feature space. So if you give me a feature map, you choose a feature map, then I can easily solve a problem efficiently in this dimension D2, which will tell me what the optimal hyperplane is. So can we use these methods for dequantization? After all, we know that all our parameterized quantum circuit models are doing is looking for the optimal hyperplane in some feature space, or they're looking for the best hyperplane in some subset of all possible hyperplanes. So why can't we just use the classical method that are known for 40 years to find the optimal one? And maybe this will outperform our variational quantum machine learning method. Okay, so to see why this may or may not work, we have to do a quick theory. We have to do a quick recap of the complexity of different kernel-based methods. So firstly, imagine that we just want to find the best linear separator in our original data space. What we can do is linear regression. This is somehow optimization method 101. And so there's no feature map. The data is just living in some Euclidean space of dimension D1. And so finding the optimal hyperplane you can do very easily, and it has a space complexity which depends on the number of data points and the dimension of the space. And the time complexity is also polynomial in the number of data points and the dimension of the space. Okay, but now we know that the data might not be linearly separable, so we want to choose a feature map which maps into a higher dimensional space. And of course, in this higher dimensional space, we can just run linear regression again. But now we're in this higher dimensional space, and so we have a complexity which is linear in the number of data points. But now what comes in is not the dimension of the original space, but the dimension of the higher dimensional space. Okay, so the point is these methods are efficient when you use the dimension of the space as the measure of efficiency, and the time complexity is also polynomial in the number of data points and the dimension of the space. Okay, and then there's kernel regression. This involves kernels. I'm going to skip this for now. Okay, so here's the first idea for dequantizing variational quantum machine learning. Instead of running variational quantum machine learning, why don't I just simply run a classical linear regression using the feature map defined by parameterized quantum circuit? So what I mean here is someone gives me a quantum circuit, a parameterized quantum circuit. I can immediately calculate all the frequencies occurring in the weighted sum representation. From that, I can immediately do the cosine and sine decomposition. This defines a feature map, and now I can run the linear regression, and I'm guaranteed to find the optimal hyperplane with respect to that feature map. And I mean, like already we've said before, that parameterized quantum circuits are only exploring a subset of hyperplanes with respect to that feature map. So surely this should do better than running variational quantum machine learning, and I can do all of this on my classical computer. So you've given me the quantum circuit, I've calculated the frequencies, and I run this method, and it should, in principle, perform better than your variational quantum machine learning ever can do. So remember, we have the set of linear models with respect to this feature map, which is defined by the data encoding strategy. We have the set of all PQC models. Now we could either run PQC optimization and find some hyperplane, so some vector W, which defines a model. Or what we could do is linear regression with respect to the feature map and find some other hyperplane, which might do even better with respect to the data than the PQC optimization does. Okay, so remember though that our feature map took us from the original data space into some new data space, which is 2 times some capital D, where D is the number of frequencies, because for each frequency you have a cos term and a sine term. So basically the dimension of our feature space is 2D, where D is the number of frequencies that came out of the weighted exponential sum representation. Okay, so now we can see immediately that there's 2 problems to this dequantization idea. The first is that the classical method suffers from exponential complexity. So this is code for it's slow and it's bad. So we know already that the complexity of the linear regression depends linearly on n and the dimension of the feature space capital D, and the time complexity also depends polynomial on n and the dimension of the feature space. But the problem is that the dimension of this feature space is the same as the number of frequencies, and this is exponential in the dimension of the original space. And this is because remember that our frequency set was this Cartesian product. And so if each one of these, if there are D sets in this Cartesian product, and each one of them has n frequencies, remember we saw that if you use Pauli matrices, then you get all the frequencies from minus n to n. So there's approximately n frequencies, and then in each set, and you take the product, you end up with an exponential number of frequencies. So it's linear. The complexity of this linear regression is linear in the dimension of the space, but the dimension of that space is exponential in the dimension of the original space, which is the thing that we care about. And the second thing is that these models might have poor generalization. So what we actually guaranteed by the theory of kernel methods is that this X that we find is guaranteed to do better on the training data. But we don't actually have any guarantee about the relative performance of these models on the test data. And so we know for sure, we are able to prove easily that the model that comes out of classical linear regression does better on the training data, but it could be that it overfit. And it could be that because of the sort of constraints of optimizing within the subset, you end up doing better on the testing data if you're not able to express any model, in particular a model that overfits. Okay, so now can we come up with a solution? So now we've said here's an idea for dequantizing quantum machine learning, but it has these two issues: exponential complexity and poor generalization. And can we come up with a solution to these problems? And there's a method called random Fourier features, which might be just us, which might do the trick for us. So remember that this feature map is this kind of map which consists of capital D pairs of cos and sine terms, each of which is determined by a different frequency that appears in the frequency representation defined by the data encoding strategy. So what happens if instead of using this entire feature map, what we do is we define some probability distribution over the frequencies. And instead of using the whole frequency map, we just sample m of these frequencies at random, and then use the approximate feature map, which only uses the frequencies that we've sampled random. Okay. And then we could just choose m to be some polynomial that we can do efficiently. And maybe these things have the property that this is a good estimator for this full feature map. And then statistically, we're going to do just as well using this as we would using this, but we're efficient. So this is the idea of random Fourier features. Okay, now we can prove a theorem, and this is something that hasn't actually appeared yet, but it should appear in a paper that comes out next week or so. We can prove that linear regression with random Fourier features, in other words, when you use a randomly selected approximate feature map, is guaranteed to output a model which is no more than epsilon worse than the one that you get from PQC optimization, provided that the number of data points you have is greater than whatever this thing is here, and I'm going to describe it soon. And the number of samples that you take is greater than this expression here. So of course, at the moment, you don't know what this means and what that means. But the key thing is that I've made a mistake here, that this T omega, there's some operator T defined by omega, and its norm depends on the probability distribution over the frequencies. And this thing here is, so F star PQC is the optimal PQC model, and its norm, which determines the number of samples you need to take, depends on the alignment of the optimal function with the probability distribution. Okay, so at the moment, this is completely impenetrable, but we're going to go in more detail into what determines these things. You just have to know that there's some quantity that we can define clearly, which determines the minimum number of data points and samples you need to take to guarantee that the classical model you use is as good as the PQC model. Okay, so now let's just quickly see, when will this random Fourier features based dequantization be efficient? Well, it'll be efficient if we can efficiently sample from the distribution of the frequencies P that we choose. And it will be efficient, in other words, the number of samples that you need and the number of data points that you need and the number of samples that you need will be efficient, if and only if whatever this thing is here scales polynomially in D, as well as whatever this thing here is scales polynomially in D. Okay, so let's look slightly more detail at these quantities. So we have this probability distribution over frequencies, and it turns out that 1 over this operator, so there's this operator T, and this object that we care about is equal to 1 over the maximum probability distribution. So basically, in order to prove that the number of data points that we need is only polynomial, we need that the maximum probability is at least polynomially an inverse polynomial. And basically what this means is that the distribution has to be concentrated. So for instance, to give you an example, in the uniform distribution where all the probabilities are equal, they're all 1 over n to the power of D, which this means that the biggest probability is exponentially small. So in order for the biggest probability to be an inverse polynomial, what you need is that the distribution is concentrated. So the example on the other end of this is if you just imagine one element with probability 1, then clearly the biggest probability distribution, the biggest probability is bigger than an inverse polynomial. So the message that I want you to take away is that in order for this to work, this distribution over frequencies has to be concentrated. Then we can imagine also, using our knowledge of Fourier decompositions, we could take an inverse Fourier transform of the optimal PQC model, and we could ask about the weights of the frequencies that appear in this frequency representation. And we can define a distribution from that. And it turns out that this thing here, the like norm measured with respect to the probability distribution P of the optimal PQC model, measures the alignment between the probability distribution we choose and the frequency representation of the inverse Fourier transform of the optimal function. And the thing to take away is that this thing is going to be small. And in other words, remember that this thing determines the number of samples we need from this probability distribution. This is going to be small only when these two distributions are well aligned. Okay, so I can summarize by saying that there are two very important objects you have to take in mind. The one is the probability distribution you choose over the frequencies appearing in this representation. And the other is the probability distribution defined by the inverse Fourier transform of the best possible PQC model. An RFF-based linear regression is going to be an efficient dequantization method when this distribution P is concentrated and efficiently sampleable, and when it's well aligned, in other words, when it looks similar to the distribution defined by the inverse Fourier transform of the optimal function. Okay, so now we can make some conclusions from this whole exploration. The first thing is that PQC models for classical data have a very useful representation as a partial Fourier sum. And we saw that this is useful because it immediately allowed us to prove, for example, that these models are universal. However, we can also use the exact same representation to prove that there exist machine learning problems and PQC architectures which can be provably dequantized via random Fourier features. In other words, we can prove that there's problems for which you can choose a probability distribution P over frequencies, and for which the optimal function is very well aligned with that. And for these problems and architectures, there is no point to using parameterized quantum circuits because you can just use do linear regression with randomly sampled features. However, we can also show that there exist problems in PQC architectures which can provably not be dequantized. And the way you do this is by considering problems whose optimal function is a uniform distribution over frequencies. And therefore, if we want the probability distribution over frequencies to be well aligned, it also has to be the uniform distribution, but then its biggest probability will be too small for this procedure to work. And so one of the main contributions is identifying concrete problems in architecture metrics which determine the potential of dequantization. So they tell you when you may or may not expect these methods to work. Okay, and that's all I wanted to say. It's basically been an hour. Thanks for listening. And it's also important for me to say that I've been lucky to have many great collaborators. Johannes, Elias, Sofiane, Eric, and Jens are in Berlin. Maria's sitting in Durban with you guys, and Bryce is at IBM with me at the moment. Okay, thanks. I'm happy. I know I've taken up the entire hour, but I'm happy to take any questions that anybody might have.
Yeah, thank you very much, Ryan, for the excellent talk. I don't know if you heard the live clapping. Let's see if there is some visual clapping from the online audience. Yes, here it comes. Wonderful. So now it's time to ask for questions, and I would like to encourage our online participants just to raise their hand, and I can give them the right to ask their question in person. Let's start maybe with the audience here. Any questions? Okay, please, Matt, let me give you a microphone. Here we go.
Thanks, Ryan, for the nice talk. I have a question on your ending slide about how this gives us kind of architecture metrics for what is dequantizable or not. Is there any insights in like the actual like layout of the unitaries or the gates on the circuit, like that kind of architecture, how that maps to whether you can dequantize the circuit that way or not, whether there's like an efficient or a nice linear regression model.
Yeah, that's a great question. So the very nice thing, so we have this result here, which says that that all models of this type, all PQC models of this type have this representation. The very, very, very nice thing about this theorem is that it has absolutely no dependence on where the gates are. So you can put these data encoding gates at any point you want in the circuit, and you can put the trainable gates at any point you want in the circuit, and you will still have this theorem holding. And so what this means is that one immediate thing that you can say is that you should not have a data encoding strategy that only realizes polynomially many frequencies. Why? Because remember that one of the obstacles to linear regression was that where is it here? One of the obstacles to linear regression was that the frequency set, I don't know where the slide was. I can't find it. Anyway, it's fine. Like one of the obstacles of using classical linear regression was that there's an exponential number of frequencies. So if you choose a parameterized quantum circuit architecture that only has a polynomial number of frequencies, this can be immediately dequantized. That's the first thing. The second thing is that yeah, so I think that's the main sort of takeaway. The second thing you could think about is, and this is something that needs more, there's a lot of open questions here. So remember I said that we don't really understand how the coefficients depend on the trainable gates. And it could be that there's classes of architectures such that the optimal PQC function is always concentrated on only a polynomial number of frequencies. These are also terrible, because then you know that there's a concentrated distribution that you could choose, which is well aligned with the optimal PQC model. So I would say these are the two takeaways. You need to have at least an exponential number of frequencies, which means that the number of encoding gates should at least scale linearly with the number of features of the data. And we need to do more research into the effect of these trainable gates on the coefficients to make sure that they're not always concentrated on only polynomially sized subsets of the frequencies. I think those are the two kind of succinct insights that I could draw. Yeah.
Cool. Thanks.
Thank you. There is a question by Alessandra, who joins us
from
Verona.
From Verona. Can you hear me?
Yes, please.
Okay, good to join this very nice meeting. Hello, Ryan. Nice to see you. I just have a question but before I want to ask you about, at the very first slides, you define the parameterized quantum circuit. And there you talk about x and theta being parameters. And I don't understand why you call x a parameter. In general, when you do this kind of training, which is like the classical neural network, the parameters are those that are variationally optimized, right? So the theta and x is typically called the input, the data input. Mm-hmm. So it is not a parameter in the sense that it is not optimized. So just to be sure that, I mean, x is the input data, right? So I would have some problem in as a classical machine learning coming from classical.
For sure. Okay, I mean, I understand your question. You're completely right. The only parameters which are optimized during optimization are the thetas. And the x's are fixed. Like you give me a bit string that is the input, and that fixes these gates. The point is that these gates are parameterized by the data in the sense that they can take any value, but the value that they're going to take is determined by the input that you want at this time. I mean, maybe I can make some analogy for you.
Just it makes a confusion with respect to what in classical machine learning is called parameterized and non-parameterized method. And here we are talking parameterized.
You're totally right. Yeah. Okay, these are parametric methods. And the only trainable parameters.
Just to be sure that we are on the same. So x is actually the input data. And then I wanted to ask you something about the dequantization. So at the end. So if I understand correctly, you want to introduce a kind of, so to say, use some kernel or like optimization to within the space of parameterized quantum circuit. If you go to the one of the last slides, maybe.
Yeah, this is a good one.
Yeah, exactly. So you do a kind of linear regression within, you know, the space of the PQC models. Okay, so what you want to get here is essentially to understand which model can be considered to get an advantage and to, you know, rule out all the rest. But in terms of getting advantage with respect to classical deep neural network, that's I mean, that's all possible. I mean, we are still within the linear models, right? So it's like making a kind of reasoning which parametric quantum circuit are better than others, but you can't compete anyway with the classical deep neural network. Is that correct, or I'm wrong?
Yeah. So the way that I think about it is as a sequence of hurdles. So in order for parameterized quantum machine learning to be useful, there's some hurdles that it should jump over. Firstly, it should do better than classical machine learning on extremely unrealistic problems that, like, where you take the discrete logarithm and you embed it into a data set. Okay, it passed that hurdle. Now, the next hurdle that all the PQC models should take is they should at least do better than extremely simple linear regression in feature space. And at that hurdle, some of the PQC models, they fail already. And now some of them make it through, the ones that can't be dequantized by simple linear regression. And now we know that those are the ones we should focus our attention to. So you can think of this work as just one step in a funnel that we're putting all the PQC models through, and we're interested in which ones come out at the end, because those are the only ones that we should consider seriously. And you're right that those ones which make it through this hurdle, I still have no idea how they compare to state-of-the-art neural networks, but I at least know that I can't dequantize them using linear regression very, very simply. But you're totally right that the ones that can't be dequantized in this way could easily do much worse than neural networks. But now at least I know that if I want to prove that, I can focus on the subset of models which can't be dequantized by linear regression. Yeah.
Thank you.
Pleasure.
Thank you, Alessandra, for the question, and Ryan for the answer. Are there any more urgent questions? I think it's past 5 o'clock. So Ryan, thank you very much for the excellent talk. I hope we will stay in touch.